Preview of the part 2 of the lecture video on the topic Doppler physics made easy. Short clippings of the various parts of the lecture video will follow. Having gone through the preview, if you wish to listen to the main lecture video, go to sonoshare.in.
The next display is the spectral waveform. So here you take this example. Now here this is as a curve. It is like the ECG pointer. So each the sample volume is like the ECG velocity is 60 centimeters per second. So the velocity information is known, and the last information we get is the nature of flow. So that is assessed by this line, the spectral line. The sampling is done only in that area. How is this done? Suddenly the gate opens, so this goat alone can go inside this part of the fence. So similarly, the coming back wave will be allowed at a reach the analyzing area of the probe. But whereas when the reflected wave from this vessel comes, the gate here it uses centimeters per second. So we are not going to analyze kilohertz, the Doppler shift, but we are interested in the velocity of blood flow. So the machine converts the kilohertz to centimeters per positive and negative, that is positive velocities and negative velocities. So the Nyquist limit is positive is 120 centimeters per second, negative is 120 centimeters per second. But you can shift the baseline downwards. Okay, wall filter of 60 hertz. So as a result, the the low velocities, which is the flow velocity in the umbilical artery is low in the diastole. So that is flow in the umbilical artery. But because you have used the wrong wall filter of high 500 hertz, then the sample gate should be center of the stream. In an artery, it should be centered because of the laminar flow. We get the laminar velocity spectral Doppler. So for artery, you use a small sample volume at the highest flow. So here, so wherever there is flow, it will be shown in the spectral Doppler. Okay, so this is useful in certain situation. In obstetrics, we have to put the sample volume through the SVC and heart block. So to study the simultaneous information from atrial and ventricular events. That here the gain is more. You get these artificial echoes, and then proper gain and low gain. Calculate the convert the Doppler shift into centimeters, the velocity of blood flow. It is done by using the Doppler shift equation, which contains the theta, that is the Doppler angle. So this Doppler angle information you have to provide to the machine, and you see the velocity is 43. You see the difference, 73 and 43. So if you don't give the machine information about the correct Doppler angle, you will measure the peak systolic. Studied velocity is more than the Nyquist limit. We get there is no place on this side to represent that velocity, so it wraps around and displays the increase in PRF as well as shifting the baseline. It doesn't get corrected, then you have to shift to a lower frequency, reversal of flow in the vessel. So it is shown below the baseline, and then again late distally we get a positive flow because of the compliance of the vessel. So the vessel during systole it becomes broader, and once the heart pumping stops, the vessel walls come back to it, so that you get the low resistance flow here. What are the characters? It is monophasic. It is seen only on above the baseline, and it has a low peak. Peripheral vascular resistance is not very high. We don't get the flow reversal, so it is monophasic. But resistance is optimum in between, so you get in the internal carotid artery. So this is the signature of internal carotid artery, and this is the intermediate resistance flow pattern seen in the non-gravid uterine artery. Okay, so that is the low resistance flow pattern which happens in the uterine artery normally, because it is because of pregnancy. So it is a physiological increased greatly. So this happens in placental dysfunction. So this is abnormal. This is not normal. So this is a pathological change in the signature of the, that is the SD ratio or resistivity index or pulsatility index by mean velocity. So these are the three ratios. So that is why when we measure the ratios in the uterine artery, umbilical artery, MCA, measure by peak systolic velocity, angle correction is necessary, mandatory, because the machine needs the time. So the spectral line thickness, that is the whether it is thin or thick, will reflect the velocities, the range spectral broadening. So this happens when there is stenosis, and distal to stenosis we get range of velocities. So as a result, this line becomes broader, fill the first peak, that is the end of systole. The time taken is called the acceleration time. So when it is normal, the acceleration time is low, but when there is by the pattern of flow we get, we can say the status of the distal vasculature, that we get in the when it is we get reflection of the peripheral vascular resistance. That is what we get. And uh, the flow decrease will be very much reduced as shown here. So that is the critical level. So there you diagnose, we get a very obvious change in pattern of the spectral range of velocities, and there is also change in direction of blood flow, that is the high velocity, and there can be color bruit around. So these are the features of color Doppler studies. So that fills the spectral window, and there is turbulence because there is also change in direction of flow here at the edges. So that is reflected well. So when there is flow distal to when the stenosis increases further, very close to total occlusion, the velocity, and there is no diastolic flow, and this happens just proximal to very severe stenosis. So see here the delayed upstroke, it becomes and a rounded peak and a very low velocity because it is a collateral flow. So it is or absence of an aneurysm, whether true or pseudo aneurysm, and that is the information you get in grayscale. Color Doppler, we get information in a larger area, and quickly we get the velocity changes. Okay, so that is the difference between color and spectral. So to conclude, color and spectral Dopplers are complementary. We need color reflected as color bruit, and artifactually we may get absence of flow as seen here because of the shadowing due to calcified plaque artifact, which helps us to diagnose that that is a calculus. Okay, that is the artifacts both in ALIASING. So ALIASING is because of the Nyquist limit. Here there is no limit of PRF, so no Nyquist limit, so there is no ALIASING, but we will not get spatial resolution and get better filling of the vessel. But the disadvantage is flash artifacts. We can use this power Doppler for low settings. We have to use as per the presets allowed in the machine. So that is ALARA principle. Thank you.